So today we're going to be trying to put together everything that we've kind of talked about for the last 4 days. So last week we learned how we can talk about angles that are larger than 180 degrees, are larger than 360 degrees, and what does that actually mean? And what does negative angle mean? And it all comes down to we're thinking about these angles on a circle and its rotation. We're spinning around the circle. And so if we're going counterclockwise, that's positive angle movement. And if we're going clockwise, that's negative angle movement. And we did this because ultimately we would like to talk about sine and cosine, which we reviewed yesterday, as functions. And if we want them to be functions, then we need to be able to use, the whole number line, all of the real numbers, the positive and the negative, and the larger than 360, and all the little decimals and everything in between. So we want to be able to use all of the real numbers if we want to make sine and cosine a function. Well, as we reviewed yesterday, sine and cosine and tangent are ratios for sides of a right triangle. And if we're dealing with right triangles, well, right triangles can't have any angles bigger than 90. That's even more restricted than just, thinking about 360 degrees in a circle. So how do we talk about angles that are larger than 90 degrees if you can't have a right triangle with angles that are larger than 90 degrees? And so that's what we want to talk about today. How does sine and cosine and tangent fit into angles if we're talking about negative, positive, and these large angles? So we want to remember that we kind of last week transitioned to thinking about angles on the coordinate plane. So we talked about how we always start here on the positive side of the x-axis at 0, and that we rotate counterclockwise, and this is how our angles are kind of spinning around the circle. And so that is really the basis for all of our sine and cosine and tangent functions. So if we think about an angle, we'll start with one that, works out nicely, 45 degrees. We know we can do sine and cosine and tangent with 45 degrees. But if we're thinking about it on this circle, how do we do that? And the reason is if you have your angle, we know that our initial side is right here at 0, but our terminal side always comes up here, and it touches the circle somewhere. And that's where we get that angle that we're dealing with. Well, if at that point on the circle, if you just drop a vertical line down here to the x-axis, what it gives us is a right triangle. And so this is what is the right triangle that we use to actually do the sine and the cosine and the tangent. And so what that also very conveniently turns out to be, if you think about this point on the coordinate plane, when we do coordinates for a point on the coordinate plane, we do x and we do y. X is how far it is from the origin horizontally, and y is how far it is from the origin vertically. So if we think about that on this right triangle, the x coordinate of this point actually turns out to be this side of the right triangle, this leg of the right triangle. And this y coordinate of that point on the circle actually turns out to be this leg of the right triangle. And then the hypotenuse of the right triangle is always just the radius of the circle. And that gives us all three sides of the right triangle that we need in order to find the sine or the cosine or the tangent for that particular angle, whatever this angle might be. And that angle doesn't have to be 45. It can be any of these angles in here, between 0 and 90 degrees. So when we're looking at these points for these angles on the circle, what we find out is that the sine of the angle is always equal to the opposite side. So in this case, that would be y over the hypotenuse, which is the radius of the circle. Cosine is always equal to the adjacent side, that's the x here, over the hypotenuse, which is the radius of the circle. And so what we learn about circular trigonometry when we're thinking about the angles and dealing with angles on the circle spinning around the coordinate plane is that if we want to find the sine of an angle, it's going to be its opposite side over its hypotenuse. And if it's the cosine, it's the adjacent side over the hypotenuse. Well, that turns out to just be whatever that coordinate for that point is divided by the radius. We can also, and you'll see this in Math 4 and pre-calculus, we can also find the x and y coordinates. Sometimes we know the sine of the angle and the cosine of the angle, and we actually want to figure out what is the coordinate of the point. So if you solve it for x and y, we get that x is equal to the radius times the cosine of the angle, and y is equal to the radius times the sine of the angle. And so that's where we get that these coordinates are equal to that. Well, that's great when the angle is in this first quadrant, quadrant 1, because I can find the cosine of 45 degrees. I can find the sine of 75 degrees. You know, those are right triangles. We can find those things. They're saved on our calculator and all that kind of good stuff. But what does that mean when it's in one of these other quadrants? And so what we have in this case is we have to realize that, yes, when we're dealing with the angles, we're thinking about this angle right here. You know, we're spinning around, and so this is the larger angle here, like 120 degrees or 135 degrees, whatever happens to be that angle over here in the second quadrant. This is the angle we're talking about. But when it comes to sine and cosine and tangent, we have to have a right triangle. So just like we did over here where we dropped a vertical line down to the x-axis, that's what we do on this side as well. So even though this is the angle that we're finding the sine or the cosine or the tangent of, it's really this right triangle that we're dealing with as far as opposite and adjacent and hypotenuse. And so we end up with like an angle here. And this is what you guys were doing on Friday, finding reference angles. This is what a reference angle is. In order to find sine and cosine and tangent for these angles that are larger than 90 degrees or negative and going in the other direction, what we have to do is we have to find the right triangle from quadrant 1 that is associated with it. And then we're just going to reflect it. Notice that all this right triangle is a reflection of a right triangle over in this quadrant. So the sine, the cosine, the tangent, all of that is going to be the same. The only thing that changes is when we think about the coordinates in this first quadrant, coordinate points are always positive, positive. You know, the x is positive and the y is positive. But when we reflect over to this side, if we're dealing with coordinate points on the circle over here for these larger angles, in the second quadrant, the x-coordinate is actually negative, and the y-coordinate is positive. Down in the third quadrant, the x-coordinate is negative, and the y-coordinate is negative. And in the fourth quadrant, the x-coordinate is positive, and the y-coordinate is negative. And so over here, where we figured out that sine and cosine are the x and y values for these points, that's going to be the case for all of our sine and cosine values. They're going to always be the x and y coordinates. So the only thing that changes when you get to angles that are larger than 90 degrees is we're flipping the triangle over to the appropriate quadrant, and it just changes the positive and negative of the sine or cosine. And this is why if you go into your calculator and you type in sine of 135 degrees, you get a positive sine, but if you type in cosine of 135 degrees, it actually turns out to be a negative number. And you're like, well, how can cosine and sine be negative numbers? Well, it's because they're on the coordinate plane. You know, it's still dealing with a right triangle, and it has that reference right triangle over here that all the sines and cosines are based off of. So we only have to do the actual trig ratios in this first quadrant. Then it's a matter of flipping everything and figuring out what they match with over in the other quadrants, and they have the same value. They just might change positive or negative. Now, a phrase you may have heard before is the unit circle. And this is going to be a huge deal. You need to spend quality time memorizing certain parts of the unit circle. We know that similar triangles that have the same angles, they have the same sine, cosine, and tangent ratio. It doesn't matter how big the triangle is. Once you do that ratio of opposite over hypotenuse, it always turns out to be the same ratio as long as the angle is the same. So we could do sine and cosine with any radius circle. We could do any size triangle we wanted to. The sines and the cosines were going to be the same. So as mathematicians, we of course choose the easiest radius to do any of the math with, and that is if the radius is equal to 1 unit. Why make our life hard and pick a circle that has a radius of 23, when if we just choose a circle with a radius of 1, then I'm always just dividing by 1 or multiplying by 1, and I actually get that whatever the sine value of that angle is, it is the y coordinate. I don't have to multiply it by anything. The cosine is the x coordinate, and I don't have to multiply it by anything. All I have to know is what are these points around the circle, and I know the sine and the cosine for that angle. And so this is actually what we use the unit circle for. It helps us to find exact values of sine and cosine. I know you're used to, we just use the calculator and type in sine and cosine, and it gives us this long decimal irrational answer half of the time. Sometimes it's a nice, neat, rational number, but we get all these decimals. Again, mathematicians don't like approximations. We like exact values. So as you get into Math 4 and pre-calculus, and then when you move on to NC State, you have to have exact values for the sine and cosine. Plus, at NC State, they don't let you use a calculator. So we want to make sure that we have a calculator in our head that we can use to find these sines and these cosines, and that is the unit circle. So we're going to talk about now what is the unit circle. We're going to fill out the unit circle, and we're going to talk about this sine and cosine and where all these points on the circle are so that we know the sine and cosine for all of these angles. So we want to start by just thinking about a blank unit circle. Things that we want to realize is that, of course, the origin is the center of the circle, and in the unit circle, the radius of the circle is 1. So that means that our points on the circle that actually land directly on the x and y axes, those points are pretty easy to find. This would be the point 1, 0. And this would be the point 0, 1. And then that makes this one -1, 0. And this one would be 0, -1. So we get those 4 main points because they cross right over the axes. And since we know the radius of the circle is 1, we know those points exactly. And we have those coordinates. And so that's kind of where we start our unit circle. What we want to do on the unit circle is we want to find the coordinates of all of these points where they touch the circle. Because if we can find those coordinates, we know that the x-axis is equal, the x-coordinate is equal to the cosine of that angle. And the y-coordinate is equal to the sine of that angle. And so this becomes our calculator. If I know what these points are, I know the sine and the cosine for that angle. Now, we obviously are not going to spend our time finding the infinite number of angles that go around, because you could have every decimal of an angle, 360 at the very least. But we do have main angles that we use a large portion of the time. And so we do want to find kind of those main angles. These are the big 3, so to speak. That is 30 degrees, 45 degrees, and 60 degrees. And then that's in each of the coordinate or each of the quadrants, because remember, we're going to take this right triangle and then reflect it over here. So this angle over here has the exact same sine and cosine. The only thing that's going to change might be the positive and negative part. So then when you reflect this one down, this angle has the same sine and cosine numbers, but again, the signs change. And this one gets reflected down. So this point is going to have the same coordinates, just sign changes. And so that's why we can do the math in this one quadrant, but then it's going to translate over to these other quadrants as well. So when we look at a 30-degree angle, we know that the hypotenuse is 1, and this is one of the reasons that we did spend time doing the special right triangles. We know for a 30, 60, 90 triangle how to find the other two sides of that right triangle. We know if the hypotenuse is 1, then the short side is half of that. So it's just going to be half. And then we know that to get the long side, we have to multiply the short side times the square root of 3. So that gives me the square root of 3 over 2. So I know all three sides of that special right triangle. So the coordinate of this point is square root of 3 over 2, 1/2. And so I know that the cosine of 30 degrees is square root of 3 over 2. And I know that the sine of 30 degrees is 1/2. We also want to keep in mind that not everything's going to be in degrees. We also have radians. And so if I'm counting by, let's see, we know that half of the circle is pi radians, or 180 degrees. And if I'm doing 30 degrees, then I'm breaking this half of the circle up into 6 equal pieces. So we're counting by 1/6. So this would be pi over 6 radians. This one would be 2 pi over 6 radians. This one was going to be 3 pi over 6 radians. This one will be 4 pi over 6 radians. And this one's going to be 5 pi over 6 radians, because then I get to 6 pi over 6, which is just 1. Now, of course, some of these fractions do need to be reduced, but I was just counting by 6. It's really easy to figure out what your radians are if you just know that 30 degrees is 1/6. So if I count around the circle on all the 30 degrees, in fact, I can do 30, 60, this would be 90 degrees. This would be 120 degrees. This is going to be 150 degrees. And then you get your 180. And then we can keep going. It's still counting by 30s. So this would be 210 degrees. This would be 240 degrees. This is 270 degrees. This is 300 degrees. This is 330 degrees. And this is 360 degrees. And so you just count around by 30s. I don't memorize what all these angles are. I've been doing this for over 20 years, and I don't memorize what these angles are. I memorized that I just have to count by 30. So count by 30s. I also just memorized that I'm counting by 6. So 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. That makes this one 7/6 pi radians, and this one will be 8/6 pi radians. This is 9/6 pi radians, 10/6 pi radians, and 11/6 pi radians. Now I'll get to 12/6, and that reduces to 2 pi. And again, I do need to go back and reduce my fractions. I can't leave 8/6. It's 4/3. You know, do reduce your fractions. But I didn't memorize all of those radians. All I memorized was that I needed to count by 1/6. And even then, you don't have to memorize it if you just count how many pieces that it's dividing the circle up into. Now, the 45-degree angle, though, it doesn't divide it up into 6 equal pieces. If we think about the half circle, the 45-degree angle is just cutting it into fourths, right? So this is just 1/4. So this is 1/4 pi, 2/4 pi. That's why this one reduces to 1/2 pi. So 2/4. This would be 3/4. 4/4, which is 1. This one would be 5/4. 6/4, which does reduce to 3/2. And then 7/4. And again, when I get over here, 8/4 would be 2 pi. So I'm just counting by fourths and counting by sixths, and that gives me all of my radians all the way around the circle. And I don't really have to overthink or do a conversion to convert the degrees to a radian. So again, go back and reduce these. So 4/6 is actually going to be 2/3 pi. So, that reduces. Another one that reduces. 2/6, that'll be 1/3 pi. 7/6 doesn't reduce. 8/6 does. It is 4/3 pi. And 10/6 is 5/3 pi. And I think that's all of them that actually reduce. So after you've got all of your angles marked on here, now we can look at the different reference angles. So 30 degrees here gave us this triangle, and the triangles that are reflections of it are this angle, the 150 degrees, the 210 degrees, and the 330 degrees. These are all going to be reflections of each other. They're all the same size. They all are the same right triangle, so they have the same sine, cosine, and tangent. But because we've put them on the coordinate plane, we just have to figure out what their sines are going to be. So 30 degrees is this point. Well, I'm going to have the same point over here, but my sines are going to change. This one's in the second quadrant. So the first term has to be negative, the first coordinate, but it's still positive 1/2. So I know that the cosine of 150 degrees is negative square root of 3/2. The sine of 150 degrees is positive 1/2. When it reflects down here, it's the same point, except both of the coordinates are negative because they're down in that third quadrant where x and y are negative. So that means that sine of 210 degrees is negative 1/2. Cosine of 210 degrees is negative square root of 3/2. Same thing over here. It's going to be the exact same point, except the x coordinate is going to be positive and the y coordinate is going to be negative. So I don't have to do all of that trig over and over and over again. I really only have to know what the points are for the first quadrant and then know where they reflect into the other three quadrants. So when we're using the unit circle and when we're memorizing the unit circle, again, there's a lot of information on the circle. I'm not memorizing all of these numbers. That would be a huge waste of time. What I'm memorizing is this first quadrant. And then I can translate, use our transformations, the reflections, and put them into the other quadrants. So we used our 30, 60, 90 triangle to find this 30-degree angle, and that gave us all of these points. When we do a 45, 45, 90 triangle, and we know that its radius is 1, when we did our special 45, 45 triangles, we learned that we always had to divide by the square root of 2 to get the legs, and they're both the same. So whatever this coordinate is, the x and the y are going to be the same value because this is a 45, 45, 90 right triangle. So when I divide 1 by the square root of 2 and then rationalize it, I get the square root of 2/2. So that means its x coordinate is the square root of 2/2, and its y coordinate is the square root of 2/2. So now we just have to think of what are the reflections of this one. Well, that would be this one down here. So that means that it's going to be positive square root of 2/2, negative square root of 2/2. The other one, let's see if we come over here. This one's going to be a reflection. And so that's going to be negative square root of 2/2, square root of 2/2. And then when we reflect it down to this one, that makes this one negative square root of 2/2. That is a negative, and negative square root of 2/2. So once we know that one point, and then here we do have 7/4. 7/4 goes here. with this point, not at 11/6 with that one. This is the 7 points at this point. And we're also counting by 45 degrees. So if we did want to, let's see, this is 45, 90. So that would make this 135, 180, which would make this 225, and then 270. And then 270 plus 45 would be 315. So we have all of our 45 degree angles now. We've got is the square root of 2 over 2, square root of 2 over 2, and we just have to know the first quadrant is always positive, positive. The second quadrant is always negative, positive. The third quadrant is always negative, negative. And the fourth quadrant is always positive, negative. So now we have one more angle over here to deal with. And that is the 60 degree angle. And the good news is that it is also a 30, 60, 90 triangle. We just did the 30, 60, 90 triangle. We know that if the radius is 1, the short side has to be 1/2. And then we multiply that by the square root of 3 to get this longer side. So we get the square root of 3 over 2. The only thing that's different is notice that this time it's the x-coordinate that is 1/2. And the y-coordinate is the square root of 3 over 2. And again, when we reflect, that's going to come over here to this triangle reflects. So it's going to be negative 1/2 square root of 3 over 2. Down here, when we reflect it to this one, it's going to be negative 1/2 negative square root of 3 over 2. And then when we reflect it down to this one will be positive 1/2 negative square root of 3 over 2. I can now find the sine and the cosine for any of these angles. If I want to know the sine of 330 degrees, I go to 330 degrees and I look at its point. Sine is always the y-coordinate, so the sine of 330 degrees is negative 1/2. Cosine of 210 degrees. So if I come to 210 degrees and I want to know the cosine, that's always the x-coordinate. So it's negative square root of 3 over 2. This basically becomes our calculator. I do want to point out, though, that I'm not going to memorize this entire circle. I'm going to memorize how to find this entire circle. So I know that I count by 30 degrees and 45 degrees to get all of my degree angles. I know I count by 1/6 and 1/4 to get all of my radian angles. I know the radius is 1, so I can find my 4 coordinate points, top, bottom, left, and right. And then all I really have to memorize is what are these points here for these first 3 angles. And if we really look, there's not a lot of numbers involved. 45 degrees is always the same number for the x and y coordinate. It's square root of 2 over 2. And then 30 and 60 both use 1/2 and square root of 3 over 2. We just have to remember here the x-coordinate is longer, so it's the square root of 3 over 2, and the y-coordinate is shorter, so it's the 1/2. And here it's the x-coordinate that's shorter, so it's 1/2, and the y-coordinate is square root of 3 over 2. Once you know these 3, it's just a matter of reflecting them over to the other quadrants and changing their signs. And then you have all of those sines and cosines.